We are going to do 2016 paper 2, right? So so the first question is going to be a logic circuit question, and right, so everybody see it, right? The logic circuit in figure 1 refers to a system of 3 switches. A system of 3 switches, A, B, and C. The combination of switches illustrated below determines whether a bell X sounds. Right? We want to construct the truth table for the circuit in figure 1. So for us to be able to construct this truth table, we of course have to work out what is the expression that this circuit represents. So we can do this first part up here. And the first part up here indicates that we are going to get, let me just type it out via my keyboard, right? We're going to get A or B, right? So A or B. So we have A or B, and then down here we have not C. We have not C. So not C will meet up with A or B, but remember in this instance, right? For this instance, we have to represent our final expression with brackets around A or B before we put it with the and, because if we type A or B and not C, right? If we type A or B and not C, then what we are going to end up with is that it will want to do B and not C first. So to make sure that the A or B is evaluated before the B and not C, you put that inside of brackets. You all follow the logic here, right? Yes, no?
Yes, sir. Yeah.
All right.
Yes, sir.
Good. So we end up with A and B, A or B and not C. So now we have to construct our truth table. So we have A, right? So we have A here, we have B here, and then we have to do our parts, right? We know that we have 0, 0, 0, 1, 1, 0, and 1, 1. And the next expression that we have to, the next part that we have to follow out or to work out is to do, let's do what's in the bracket first. So we're doing A or B as an expression. And if we're doing A or B as an expression, then 0 or 0 will give us 0. Right? Let me just copy so that I have a consistent space. Right? 0 or 1 will give us 1. 1 or 0 will give us 1. 1 or 1 will give us 1. Did anybody play the game that I sent you all to work with these circuits? Anybody try the game?
So I tried it.
Yes, sir.
Okay, how you find it is?
It's cool, but it's just get repetitive after a while.
Yeah, it is pretty repetitive. All right, and the next thing that we work out is not C. And not C will give us, oh, sorry. So then in this case, I have 3 columns, A, B, and C, not just A and B. And nobody could tell me.
So I was going to ask you, but then after I see you probably doing it at the front way we didn't know before, so I was just
No. It's three columns. So
yeah,
that means that we
but
have 8 8 different inputs, right?
Yes.
I only saw the A or B, and then I decided to make the columns, but I forgot that the next input was C. Right? So we should have C. So we end up with 0, 0, 0, right? 0, 1, 0, 0, 1, right? And then we would have a whole different set of expressions here. So I'm deleting all these expressions inside of A or B and stuff like that, right? So that we would end up with it here. So 0, 0, 0, right? 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, and as we said, that these are pretty much counting from 0 to 7 in binary. Okay, which gives 8 results: 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? Sorry, gives 8 results, right? 0, 1, 2, 3, 4, 5, 6, 7. Okay, and that's 8 numbers from 0 to 7. All right, what I will do is I'll write in the rest, because this could get a little bothersome. Okay, so we want to do A or B, and A or B will give us the values of, we're looking at the columns A or B, we'll end up with 0, 0, 1, 1, 1, 1, and 1, 1. Okay, then we'll do not C. So not C is just the inverse of the C column. So where there's 0, we put 1, and when there's 1, we put 0. So we end up with 1, 0, 1, 0, right? 1, 0, 1, 0. And then the final one is the expression itself. Okay, the final one is the expression itself. So we end up with A or B and not C. And A or B and not C, we're looking at these two columns. So we're taking the result of this column and joining it with this column with an AND. So we end up with what is 0 and 1 is going to give us 0, 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0. This makes sense?
Yes, sir.
Good. Good. So this is the truth table for the circuit in figure 1. All right, so the next question, let me pull it up. Next question asks us to, construct a truth table for the proposition P or Q, right? I'm going to copy it in now, so don't panic. So again, they followed up a truth table question with another truth table question. In the space below, construct a truth table for the proposition P or, sorry, that's P and Q, not or Q. Right? So we have, again, we have P. This one could be done very quickly. P, Q, right? If we have P and they represented it using this propositional logic that's at the back of your that's at the back of your syllabus. Again, we have 0, 0, 0, 1, 1, 0, 1, 1, right? And because this is AND, this one is AND, we end up with 0, 0, 0, 1. So that question was with 4 marks. Right. The next question is, what is a program counter? Okay, so what is a program counter? a program counter. Let me put it in the open board. All right, so what is a program counter? Program counter is the register in your CPU that keeps track of all the instructions. The program counter is the register in the CPU that keeps track of all of the instructions that are to be executed by the processor. All right, so that's the specific name of the program counter. That's the specific name of the program counter, the register that keeps track of all of the instructions that are inside of a computer system. All right, we're moving on. All right, so next up we have some binary numbers. All right, next up we have some binary numbers. So below are two 8-bit binary numbers stored in registers 1 and registers 2 respectively. When the numbers are added, the result is stored in an 8-bit register, register 3. Right? The result is stored in an 8-bit register, register 3. So we have these, add the two numbers and explain what will be stored in register 3. So we have 1 0 0 1 0 1 1 1, and we have 1 1 0 1 1 0 0 0. Okay, and we want to add these two numbers, and we know our binary addition, right? We remember that of course 1 plus 0 is 0 1, right? 1 plus 1 is 1 0, and 1 plus 1 plus 1 is going to be 1 1. Please excuse me a second. Right. So 1 plus 1 plus 1 is 1 1. So let's do the binary addition for this one. All right, so 1 plus 0 is of course 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 will give us 1. 1 plus 1 will give us 1 0. 1 plus 0 is going to give us 1. 0 plus 1 will give us 1. 1 plus 1 will give us 1 0. So we'll end up with an extra 1 here. What is going to be stored in register 3? And they are 8-bit registers. The question specified that they are 8-bit registers. So what is going to be stored in the 8-bit register, register 3, is going to be this value of 01101111, because you have 9 bits, but you have an overflow. This bit is an overflow and cannot fit into the register, register 3. Do you all understand what we did here?
Yes, sir.
Right? So the question here is asking you to show what would be stored in register 3. Because register 3, right? Because register 3 could only store 8 bits, then what is inside of the square will be stored inside of register 3. So the next question is going to be a decimal to binary floating point question. And what they want us to do is to convert the decimal number 13.25 to binary, right? 13.25 to binary. Do you all remember how to do this? Okay. So again, let's just...
On how to do a question.
Sorry?
So it's so you like you're taking the 13 as a normal number to convert to binary, and
Right.
you're doing the 0.25, but I believe you're just like multiplying it by 2 until you get 0.5, and after that you just doing the same thing. You're taking like the remainders and adding it to the end of the value of whatever 13 is in binary.
All right. All right. It sounds correct. Let me go it over with you all. Remember we talked about the point here, right? So we have this is our point here, and we know that we have 1, 2, 4, 8 going forward here. And then we have half, quarter, 1/8, etc. going here, right? So let's take a look at converting this 13. 13 minus 8, 8 could go into 13. Yes, 8 could go into 13 once. So what we left with, we have 13 minus 8 is going to be what? That's 5, right? Could 4 go into 5? Yes, you have one value of 4 going into 5. So 5 minus 4 will give you a value of 1. Could 2 go into 1? No. Could 1 go into 1? Yes. Good. Could a half, which is 0.5, and this is 0.25, and this is 0.125, could half go into to 0.25? No. So we have 0 there. Could quarter go into 0.25? Yes. Right? So this 0.25 would make that 0.25. So this number is what we'll end up with. Right? 1101.01. That's how we end up with this. But remember, we have to express, well, normally we express this as by moving this 1, 2, 3, 4. So I move the point 4 times, right? So I will go 1101, right? 01 by 2 to the power of how much times did I move this? 4. And what is 4 in binary? 4 in binary is 100. Okay, if you're representing it as binary notation. So this is how we would represent this here. Okay? You all follow me here in terms of representing this number as a floating point number in binary?
So you could go over that one more time, please.
I will go over it one more time. Okay? You want me to use the same number or a different number?
So you could use the same one, it doesn't matter.
All right. All right. So we had 13.25. We start off with the floating point here, right? And we know that we have behind here, we have, right? This is, and the rationale behind it is that at the floating point, you have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Okay? And here you have 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3. And that's how I got the 0.5, 0.25, 0.125. And on this side, you have 1, you have 2, you have 4, you have 8. Okay, so things working out so far. Yeah. We
Yes,
take the
sir.
number on this side of the floating point, 13, and we break it down into binary. So 13 in binary is going to give us, right? We could do it the other way too, 13, and you could keep on dividing by 2. 2 into 13 is 2 into 13 is what? 6, remainder 1. 2 into 6 is 3, remainder 0. Right? 2 into 3 is 1, remainder 1. 2 into 1 is 0, remainder 1. Okay? If you represent it coming up, right, you get 1, 1, 0, 1. And that's what you got on this side of the point. Right? 8 plus 4 plus 1 is 13. On this side, we only have the 0.25. We have the 0.25. So we have 0 values of 0.5 and 1 value of 0.25. It's a 2 and not a 1. Right? So this is how we get 13.25 represented as 1101.01. But when we're representing binary like this, a lot of times it's more proper to present it in standard notation. So you're moving the point 1, 2, 3, 4. So this point moved 4 times. So we end up with 110101 multiplied by, right, multiplied by 2 to the 100, 2 to the power of 4. Okay?
Okay, sir. I understand now. Thanks.
No problem at all. All right? So the next question. Anybody else? Everybody else good there, right?
Yes,
Yes,
sir.
sir.
Okay, so the next question asks us about a multiplexer. What is a multiplexer? At this point, we should have the definition from multiplexer tattooed onto our brains. What is a multiplexer? If I had to say what a multiplexer was, I would say that. Anybody wants to tell me?
So that's a device or a device that could take multiple inputs and just choose one output.
Inputs and allow them, yeah, to utilize a single output line, right? The input is chosen via data which is passed in through select lines. All right. 2 select lines asserts one of 4 inputs to an output. And if we have to draw a diagram, a block diagram, to support this, our block diagram is going to look like this. All right, so this is, all right, S1 and S0. That's our 2 select lines. We have our input lines, and we have our output line. And this is a 4-to-1 multiplexer. I0, I1, I2, I3. This is your output line. Any questions?
No, sir.
All right. So let's see. Right. So let's move forward. And then the next question is, why is multiplexing important? That's a question one of you guys gonna have to answer for me here. Right? Former question, what possible use could we see for multiplexing? Why is multiplexing important?
Is important because it allows for multiple users or signals to utilize a simple communication line. For
Exactly.
example, in telecommunication, signals from multiple users' phones are multiplexed so that more than one person can communicate along a single central line.
Correct. Right? So that's a good answer. So multiplexing is important because it, of course, allows for multiple users to use the same infrastructure. Right? So multiplexing is important because it allows multiple users to exploit a single resource such as a telecommunication line. Right? In a phone system, multiple persons would access a single line or tower to send their data through. Okay, so that's why multiplexing is important. And just like that, we finished question 1 on this paper. Okay. So now we have question 2. So let me copy in question 2. And question 2 is it starts off as a super easy giveaway kind of question. Okay, so it shows the basic hierarchy of computer memory, and it requires 4 examples of specific types of memory. Wow, my pointer is stuck. Hold on. All right. Huh. Okay. Right. It requires 4 examples of specific types of memory for completeness. So we have memory, we have primary and secondary storage, or primary and secondary memory. And we have volatile and non-volatile memory. And within volatile and non-volatile memory, we have 2 types of non-volatile memory. Right? That is primary. So could you name 2 types of non-volatile memory for me, anybody? This is a Form 5 question.
ROM and EEPROM.
ROM and EEPROM. Okay, and so ROM is 1 and EEPROM is another. And the secondary storage, 2 types of memory. secondary memory.
HDD and CD-ROM.
Right. So we have CD-ROM. I put DC-ROM. And we have your hard disk drive. Okay. So questions, marks given away. Marks given away. That's 4 easy marks. Right. Next up, we have another question that is, I would describe this question as a general knowledge question in terms of it being asked in a computer science examination. Okay, you don't even have to be a computer science student to answer this question. So if we say, imagine that electricity is available but not consistently supplied in your community. You purchased a cell phone which gives 10 hours of battery power that takes 5 to 7 hours to become fully charged. Right? We have surge protector, voltage regulator, UPS. We know the difference between these, right? This question looks familiar. Did we answer this question before?
Not sure, sir.
I'm
Yes,
not sure.
So we answered all these questions before, sir.
That's what I'm saying. These questions look real familiar. Oh well, let's answer them again. So let's see who was paying attention, right? So surge protector, voltage regulator, UPS. So how can a surge protector protect us in this scenario? You just talk it through. I'm not going to write the answers. And nobody's answering me.
So
Should I
they can
call a
protect
name?
against voltage spikes.
All right, so surge protectors protect against spikes in the electrical supply. The voltage regulator does what?
Control the amount of volts it could take.
Right, so the voltage regulator regularizes the input against low power supply and spikes in power supply or surges in power supply. So whereas the surge protector only protects against like a high surge of power coming in, the voltage regulator takes an unstable signal and stabilizes it. And the UPS does what? The UPS does what?
Provides a battery backup, prevents against a sudden cut.
All right. Good. Yeah. So the UPS provides a battery backup against a sudden or a cut in power. So what I'm going to do is I'm going to jump to question 5 for when we come back from our 10-minute break. Right. So we're going to take a 10-minute break, and I'm going to jump to question 5. I'll post question 5 now so that you can watch it during the break and see. Right, because I know for a fact that we didn't do question 5. I'll post question 5 now to the board, and we could start thinking it through. Right? How would we answer this question? So in 10 minutes, I will see you guys. Okay?